So good morning everyone. So today the topic I have chosen is reflectometry for cable fault location. Actually this lecture gives just an introduction to reflectometry, not the advances in the reflectometry. Reflectometry is one of the famous method used to locate the fault, also in diagnosis of the fault. Not only that, and also to monitor the power cable health, whether there is any problem within the insulation. So for that also reflectometry techniques are used. So this lecture briefly gives an introduction to the reflectometry. So the contents of this presentation is first some introduction and what is reflectometry, then different types of reflectometry, general circuit and their pros and cons, and practical usage of reflectometry and conclusion. Introduction to this one, an underground power cables are the most, crucial part of the power systems, and nowadays there is a more tendency towards the cables, even not only in transmission but distribution. Smart city concept has come, in that we don't expect overhead lines hanging on the roads of the city actually. So underground power distribution and transmission also going to take place in a big way. Also for transmission, for a overhead line, we have to go for land acquisition, etc. For underground power cables, we don't require so much land, and once buried under the soil, so the above the soil, people can work or walk without any serious problem. So this is becoming a crucial part in the power system now. But what are the problems? The moment we turn to underground power cables, fault location and fault clearing is a big challenge actually. So identifying a fault before it occurs is very, very important. And so continuous monitoring of the cable systems is also very, very important. And after fault occurs, locating the fault is also very important. Then occurring of a short circuit fault in power cables are inevitable, yes. So there are three main reasons for short circuits: electrical breakdown, thermal breakdown due to heat of conductor and all, and electrothermal breakdown are probable reasons for short circuit of power cables. So it is very much required to pinpoint, locate the short circuit fault to reduce economic loss and also to maintain a smooth flow of power. Here some figures are shown on the right side. The metropolitan cities like Mumbai, every day around 3 power cables are having short circuited faults. This is one utility only. So per utility, roughly approximately this many failures are happening. So to dig up even for a few meters, the municipal charges are more than lakhs of rupees in, for example, in Mumbai city. So fast detection of the location of the fault is required, and accurate detection is also required. In cable, the most common fault is the short circuit fault. The most common method to locate is the reflectometry technique. Then what is reflectometry? So it is a very popular method actually. Originally it was, even now, to find out the depth of the ocean, we send some signal and it goes to the bottom of the ocean, and it comes back. So based on that, travel speed and then time at which the signal has arrived, we estimate the location, depth of the cable, depth of the ocean. Similarly, same technique is proposed for cable fault location also. Reflectometry is the process in which propagating a signal down a cable and detecting the reflections caused by impedance variations in the cable. So if we send a signal if we from one of the ends of a cable, what happens? The signal travels on the cable like a wave, and whenever it meets a difference in the impedance, there will be reflections. We'll see what kind of reflections for what kind of impedance changes we'll see in future. So this is the basic technique. The reflection study of the reflections gives us what happened, whether there is a short circuit fault or if it is there, then at what location, whether there is some problem in the insulation. So this is the basic philosophy of the method. Use of reflectometry for locating faults in a cable was first came into picture during 1982. So long back. Whenever a cable having a fault or defects, causing a change in overall impedance, and these results in reflections. So here some device is shown on which you can see the reflected waveform. Then what actually happens? In reflectometry, a low voltage pulsed signal is sent through the cable and checks for any reflections seen due to impedance mismatch. If there is no impedance mismatch, there will be no reflection, obviously. So the time and propagation velocity of the received pulse. So the reflectometry process can calculate, using that the reflectometry process can calculate the exact location of the fault. So this is what actually happens. This is a simple black diagram. This works for any type of reflectometry. There are several types of reflectometry we'll see. So a pulse is generated here. You can see this is applied to the cable assembly under test, and a load is given here. It can be open, short, or partially damaged cable. So the signal will go and then come back. So this oscilloscope will record in time scale. In time scale, both the signal which is sent also, the signal which is coming back also, both will be recorded in the oscilloscope. And you can see the duration of the gap between the sending signal and then the signal which has reflected. So based on the time, the time from time scale, you can convert it into distance scale by using the velocity actually. So distance d is equal to Vp into T by 2, because the T by 2 means the total time that is reflected on the oscilloscope is this for onward journey of the signal and for coming back. So that's why total time does not actually reflect the distance, but total time divided by 2 is the location of the fault, where Vp is the velocity of the propagation of wave and T is the transit time from the monitoring point to the mismatch. And you all know the reflection coefficient, how it is calculated. The reflection coefficient rho is given by ZL minus Z0 by ZL plus Z0. Z0 is the line impedance or surge impedance we call, and ZL is the load impedance. Load can be short circuit. So you can clearly see when ZL is 0, means for a short circuit fault. So you get rho negative, means the signal is reversed actually. So similarly, if it is a huge open circuit fault, then again it is positive under. So this is how the reflection coefficient changes with the nature of the fault also. So ZL and Z0 are load impedance and line impedance in ohms. ER and EI are the reflected and input pulse voltages. Now different waveforms observed for different impedances. You can see for open end, so it is open end, you can see the signal is same actually, because the polarity will not change. But here the attenuation etc. are not shown here, but the received signal is not same in magnitude and pulse width as the sending end actually. We'll see shortly. But just for understanding that one, for an open end you will see two pulses like this, and the gap between the time gap is double the time, because the signal has to travel and then come back. So the time taken is for onward and then return will be the gap between these two signals. So you have to convert that into distance by using the velocity of propagation. And if there is a short circuit at the cable end, other end, so you will see, just now we have seen the reflection coefficient which becomes negative. So the waveform is, uh, is negative polarity, opposite polarity to the sending end wave. Sending end we have given this kind of pulse, positive pulse, and it became, when it comes back, it became the negative pulse. So it indicates that there is a fault or short circuit here. And in case of matched impedance means there is no fault, nothing. The cable is continuous. In that case, you will not see any reflection. Only the sending end pulse will be there. No signal will come back. So just for a brief understanding, initial understanding, this is given here. Let us see the most complex situations, what will happen in actual practice. Now, just a brief introduction to these different types of reflectometry are available. We are today dealing with time domain reflectometry only, this TDR only. So in reflectometry, again, you have frequency domain reflectometry also, time and frequency domain reflectometry also, standing wave reflectometry also, and then multi-carrier reflectometry also. And in advanced latest, techniques we use, damped sinusoidal, reflectometry is also being, tried by, for example, Megger is coming up with this technique, which can simultaneously test partial discharges also. So that is the latest development. But let us today focus on time domain reflectometry. So this is the very first type of reflectometry that was introduced to locate faults in overhead conductors in 1972. So after this, around 10 years, it took for cables actually. For overhead conductors, it is introduced in 1972. A rectangular pulse voltage is sent normally, and its reflection from the fault position is being captured. And even for a small changes in the reflection coefficient, it is capable to detect the location of the fault. So what are the advantages of TDR, the time domain reflectometry? Very basic circuits required to perform, TDR. You know how simple it is, sending a waveform, sending a pulse and then capturing it, and then we have to study the various distances, only various time scale, and then convert it into distances. So capability to identify different faults for overhead conductors and short circuited faults for cables. It has that capability. Testing is easy to employ. Test equipment is very small and inexpensive. Test equipment uses low voltage, less than U0. U0 means line voltage. So very low voltage is required for this. Periodic testing provides historical data that increases the value of future tests by observing changes over time. If we continuously employ for monitoring the cable, so we can have the already recorded data, historical data. How it is, we can use it as a signature and verify, where the changes are there. So from that data, we can, easily identify the, upcoming problems, or if there is any problem in the cable and all. So that is the beauty of periodic testing and all. Locates areas of the cable system with impedance related problems. Impedance related problems means, for example, a cable which is damaged means, it is aged, for example, or some moisture ingression took place and there is some problem within the insulation, or there is local overheating which caused the insulation change. So that kind of problems may also be, if the impedance changes are enough, then that kind of changes can also be seen by observing the signature of this actually. So these are several advantages. Of course, there are certain disadvantages also of TDR. Very low signal to noise ratio. Therefore, the peak cannot be identified properly. There is a difficulty actually. Even for a millisecond delay, the actual location and calculated distance of fault can differ by 100 meters. So if it is differing by 100 meters, this is maximum value, of course. So you can imagine, 100 meters you have to dig out for a long cable, say 100 meters. It's very costly to identify the location. Of course, TDR along with additional methods are there, which will be used actually to pinpoint the location and all. So TDR is a basic method. It will give the approximate location. After that, there are several ways. For example, a hearing aid which can give us a buzz sound when the actual fault is located and all. So such kind of techniques are there. Then second disadvantage mentioned here is skilled operators are required for testing and post analysis, because we will see now just after few slides how complicated it is when there are joints are present. So an operator who actually has the knowledge of this how the reflections will occur, so that kind of persons are required to analyze the location of the fault and any problem within the insulation. There are blind spots, due to the ringing effect that occur near end. At the near end, the pulse is injected. Means blind spot means within that distance, you cannot identify the location, or you cannot identify any changes in the insulation. So the length of the cable within the blind spot depends on the injection method and the pulse width actually. So electrical noise may interfere with the low voltage TDR signal. This is another problem. Successful location of an impedance discontinuity depends on having the correct velocity of propagation in combination with the underground cable system layout. So these are some of the disadvantages of TDR. Then issues, the ability to perform the test online is unclear. Of course, in our lab we are developing a technique to conduct this test online also, and we have succeeded to some extent, and still the research is going on in our lab. So then proper interpretation of TDR data may require the history of cable system construction. The test voltage of a low voltage TDR may not be high enough to detect some dielectric imperfections. So actually in this very low voltage signal is used, because high voltage means it may damage the cable also. But if we do not use high enough voltage, what will happen is the high impedance faults. High impedance faults means the fault resistance, fault has occurred, but the impedance still remains high. Remains high means it is of course less than the cable impedance, general cable impedance, but it is high enough that you will not observe any changes. So in that case, and this adds with the attenuation and attenuation of the signal, so you cannot identify the high impedance faults actually. That is a problem. What is done normally is we make the high impedance fault a short circuit. That's how there is no other option actually. All cable companies do like that only. If there is a high impedance fault, then they will make it a low impedance fault. Means they will damage further actually. The location where the fault occurred, that they will damage further by injecting higher voltage than the system voltage, so that the location where the fault occurs gets damaged, and then they locate again. But it is kind of disturbing the system, and you are impinging a higher voltage on the system. So that is one issue. It is difficult to interpret some impedance discontinuities also. It is difficult to interpret results on tape shielded cables, etc. Selecting the pulse width for optimal resolution and distance can be problematic. Interpreting the results on circuits with multiple taps is also a challenging activity. We can see that multiple splices also how it will affect and all. So length measurements requires that the start of the TDR pulse be identified. This can also be a difficult situation. Now let us see, cable systems, conditions distinguishable using TDR. Now there are several cases how the reflected total waveform will look like. So uniform cable system with no joints. First case, this top one in the table you can see. We are injecting a pulse like this. This is at near end. Near end means where the pulse is injected, and the signal will travel on the transmission line, and then we get after it goes to the far end, and then it comes back, and this is the reflected wave that is again observed in the oscilloscope. So note that this oscilloscope is at the near end only. Oscilloscope, as you can see the in the first we have shown the block diagram of this injection, this method actually. So the oscilloscope is kept at the near end only. So the oscilloscope records near end, and then after some time t, it will record again this far end signal like this. So this is what kind of fault? This is a open circuit. The cable is open actually at the other end. So you see no reflections in between, no changes in the waveform in between. Only the near end and far end signals are clearly seen. But uniform cable system with no joints and short circuited at distance L from the near end. For example, the cable has a short circuit fault at a distance L. Then how the waveform will change? This is how the waveform recorded on the oscilloscope will change. So here there is a near end pulse, but whenever at a distance L there is a short circuit, so there is a pulse which is in the opposite polarity, because short circuit leads to opposite polarity. But you can observe here the magnitude of this this reflected wave due to short circuit is not that equal to this one actually. And there is again far end reflection again which is coming back again. So this is how the voltage, the signal that is observed on the oscilloscope if there is a fault at a distance L. And cable system with a joint at a distance L from the near end. So instead of short circuit at a distance L, if you have a joint at a distance L, because joint is also having the difference impedance than the cable system, therefore it will also cause certain reflections. So this is the kind of reflections that are observed when there is a joint. It's like this, partially positive and then negative wave will be observed. So this means that there is a joint at a distance L. And then next one is the cable system with a wet joint at a distance L from the near end. Wet joint means if there is a moisture ingression and there is some problem with the jointing. So if the water ingressed into the joint, then you will observe the modification of this, this reflected signal. For example, if we are repeatedly conducting this test, periodically conducting this test, so this kind of signature we can have with us actually. Any deviations in this position, for example at L, clearly indicates that there is a problem in the joint. So there is some moisture ingression or water ingression into the joint and the joint has failed or something like that. So this is the waveform that you observe when there is a wet joint. And cable system with water ingress at a distance L from the near end. So there is no joint here, but in the cable, due to outer jacket failure or sheath to ground fault, such kind of situations, the water will enter into the cable actually. So in that case, you will observe at a distance L, if the such problem occurs, you will observe a change in wave like this actually. So this gives an indication that there is a water ingression in the cable system. Then cable system with localized corroded neutrals at distance L from the near end. So you will get a signal like this actually. Now here on the right hand side, typical parameters of TDR pulse is given here. So this is a TDR pulse. Normally it is of bell-shaped curve actually, not pure rectangular pulse. So here you can see the pulse width is measured at 50% of the height. Because it is bell-shaped, so we have to decide, at some place we measure the width of the pulse. So it is normal practice to measure the pulse width at the 50% of the height. So this is 100% of the height, and at 50% of the height, what is the pulse? That we call as pulse width. So you can see this is the time scale and this amplitude scale. So this is how the pulse is there, and the reflected pulses are normally there will be attenuation actually. The pulse width, how it gets attenuated with different pulse widths are given here, indicated here. The attenuation is mentioned in decibels per 1000 feet here. So this is a typical graph showing the attenuation of the pulses actually. Then we will see what is attenuation first of all. So the basic definition of attenuation means reduced amplitude without changing the pulse width. So this is reduced. This is the original amplitude, and due to attenuation, the height of the pulse changes. So then, what is dispersion? So in this actually, the first one in the attenuation case, the energy gets reduced actually. What is dispersion? Dispersion is change in signal, signal characteristic, because this input pulse is having different frequencies, and on lines what will happen? The different frequencies will travel with different velocity. So the pulse whichever is injected gets widened like this because of differences in this speed of travel of different frequency components here. Then what will happen effectively? The amplitude gets reduced, and there is an increased pulse width. The pulse width gets increased, but energy remains constant due to dispersion. But attenuation causes energy also to reduce. This is kind of resistive loss, you can assume, the attenuation. And then normally attenuation and dispersion both are present on the lines. For any wave actually, attenuation and dispersion both are present, even other waves also. So which will cause reduced amplitude, increased pulse width, reduced energy. So this is how the signal looks like when this is the input signal and this may be the reflected signal. So both the pulse width also changed and then amplitude also decreased due to attenuation and dispersion. Then what is the effect of different signal widths, fast signal, slow signal, how it will happen? We can see this is the two signal comparisons are given here. One is faster TDR, this is very fast, and this is a slower TDR pulse. So you can see the pulse width is more and all here. And how the reflections will be. So there is one giant considered, splice reflection is given here. This is one giant actually. So this is giant reflection, and this is due to far end which is open end actually. This is the open end. You will see the same kind of polarity, but with attenuation. The signal. This is the signal sent are at the input end, but you are seeing, see how the signal has changed. The width, the height has changed here. Now similarly, this is a faster signal. The faster signal gets attenuated more, unfortunately. In this case, actually, in the faster case, you have more time resolution. Time resolution means the resolution in time scale or distance scale also. This has more time resolution, but it reduces the signal strength, reduces or attenuates very fast actually. So the problem here is this reduces the range of the testing. So a faster signal can be used for small range, but with higher resolution. But a slower signal will work for longer distances of the cables. But you have very less resolution because the pulse width itself is more actually. Here the pulse width is small. So here the pulse width is more. This is having one splice, or just one giant. So you can see very sharp signals like this. But here you see the one giant reflection is occupying this much space. Suppose you have one more giant, as I can see show you in the next slide. So you have one more giant here. So there are two giants here. But the problem with the in this case slower signal is that the signal superimposes on that, and difficult to identify non-differentiable signal is there. Difficult to identify the location of two giants here, but here it is very clear. So a faster signal with higher resolution can distinguish the two different giants, but it may not happen with the slower signal. At the same time, the faster signal attenuates very fast, therefore the range becomes less. Range of testing can become less. You cannot have longer cables tested using this. And but the with a slow signal, or means which has higher pulse width and all, so with that you can test for longer signals also without much attenuation. Then certain practices for TDR pulse injection. So certain considerations are practical considerations are given here. So you have, this is the TDR, generator, and you see that there is a pigtail cable again, and you have the injecting system here. So this is actual cable. This is actual cable. Now you can see clearly this has multiple impedances here. So this is the TDR system, pulse generator, which itself has its input impedance. This is ZTDR, which will be in series with that one source actually. Then TDR leads, these are TDR leads, and then pigtail. This is TDR leads. They also have certain impedance, and this is pigtail cable. This also has certain impedance, and then you are entering into the cable. So therefore, in this case, the impedances are not matching. Z equivalent is not equal to Z not cable. So Z cable, this is the cable system. So before that you have pigtail, this we have TDR leads, and then you have impedance of the source. So these are all several these things. In this case, Z equivalent is not equal to Z cable. So this is of course simplest approach. But better approach is this. Better practice is this actually. In this case, a TDR leads are connected to directly without using a pigtail cable. So here the pigtail cable is avoided. So in this case, still you have the TDR of this one, and TDR leads are there. So they will have the impedance again and the cable system. In this case also, of course, Z equivalent is not equal to Z cable. And best practice is given in the bottom. So here you use impedance coupling device and carefully decided TDR cables which have the impedance approximately equal to Z0 cable. So here impedance matching is achieved. So in this case, whatever we inject will not get attenuated in the initial, will not get divided in the initial case. Because in the other two cases, the above two cases, obviously the injected pulse and the pulse which is entering into the cable system is of different magnitude due to voltage division that will happen. So in this case, there is no voltage division. Whatever voltage we apply, we generate that voltage will be applied to the cable. So it is the best practice to conduct this TDR test. Even laboratory also you can try. You have to use the carefully designed cables, etc., lead cables, etc., to and the impedance coupling device also to match this one, and then do the testing. Then the most important thing is to understand what happens when we conduct a test like this. So you can see here clearly there are different cases actually which are studied here. This the first one is the simple case without any joints and all. Now here this graph, you may be most of you have been introduced. I think when wave theory is introduced in the power systems. But let me explain here again. So this is the cable actually. This is near end and this is far end. And this is the time scale. This is the time scale. So when we are sending a signal from here, so it travels on the transmission line at the cable actually. So this is the position, physical position at different instances of time. So this is a transmitted signal actually. Since there is nothing, this is the far end of the cable. See here, this is the near end of the cable. Since there is nothing in between, so the transmitted signal travels smoothly and reaches the far end here, and there it gets reflected. So reflected wave is given in red color. So this is the reflected signal which will travel again and then reach the far end. So now you can see what is recorded on the oscilloscope is given here at the right hand side. This is the recorded signal on the oscilloscope. So when we are injecting the pulse, you can see this is the pulse which is injected, and there is nothing in between, because whatever comes here is recorded here. Whatever comes to the near end is recorded in the oscilloscope, because the oscilloscope is kept at the near end. So this is the kind of signal you will observe, and when it reaches again, this is the signal which is transmitted and then it comes back like this. And here you observe the reflected signal again. This is the reflected signal. So since it is far end is open, it indicates that far end is open. This is the kind of signal you observe on the oscilloscope. Then there are no joints at all. There are no joints here. That's why this area is entirely smooth. There are no reflections. So there are, what is known as ghost reflections. There are no ghost reflections observed here. The reflections which occur, which are not true actually, which occur due to repeated reflections and are called ghost reflections. I will show you in the next diagrams. Then cable system. Second case is cable system with one splice located farther than 50% of the cable system length as measured from the near end. Now you see here, there is a joint. This is the joint location, here. This is the joint. So this is a joint location. You can observe just a dotted line is indicated here because whenever the signal arrives here, there will be a reflection. So now you see the joint location is more than the 50% distance from the near end. It is not, this is the middle point of the cable. You see it is more than the middle point. So it is more, the distance is more than the 50% of the cable length. So what happens? Why 50%? There is a significance actually. If it is below 50% and above 50% or exactly 50%, what will happen we will see in few next slides. So here in this case we are considering when the joint is located. Splice means joint, please. Splice is another term used for joint. So when the splice is located more than 50% distance, what will happen? So a dotted line is indicated here. Now we are sending a signal from here. The blue line indicates the traveling of the signal. This is a time scale. This is a distance scale. The signal travels like this. And when it reaches the joint, this is a joint location, right? So when it reaches the joint, there will be a reflection here. But there is a transmitted wave also. Transmitted wave continues. Of course, the magnitudes are different now of the transmitted wave. So the reflection is traveling like this and reaching the near end again at this point. So oscilloscope immediately records that. So this is what is recorded signal on the oscilloscope, right side green signal. And then this reflection is due to the joint, and the transmitted wave is continuing and reaching the far end again. From there again it is getting reflected. So this reflection is of the far end actually. So it will come back like this and reach here. So you can see this kind of waveform which is observed here. So if the joint is at a distance which is more than 50%, you don't see any other reflections within this, within this distance. So in one signal, one waveform, within one waveform, you will not see any other signals other than this joint alone. So there is no problem. No ghost reflections are observed here. Ghost reflections means, if this occurs more than once, then that is called ghost reflection. So here only one reflection is there and it will come back and it will see here you will find again this one actually. Now let us see if there are exactly, joint is exactly at the midpoint. So this is joint is exactly at the midpoint in this case. So you can see this is the length of the cable and at the midpoint the joint is there. Therefore a dotted line is drawn at the midpoint. One can, graphically do this also. So here now the signal which is sent from here travels like this and it gets reflected and comes back like this. So this reflection is due to the joint, and the transmitted signal goes further and reaches the far end. Reaches the far end, and from there is a reflection again. Now what happens is this first one, there is a reflection here due to joint, but this comes back, and from here the signal originates again. Again gets reflected at the near end also, but it is given in blue color because it is going in the forward direction. So it comes here and again at the joint it gets reflected again. So you can see here at the middle point you have only one splice reflection clearly visible, but the far end waveform gets modified actually due to combination of both, this is actually it will not be the summation of these two will occur. Actually, there will be slight difference in the far end signal which comes out here. So, but in between there are no ghost reflections that you can see. In between from here to here, there are no other reflections other than the joint here. But it becomes complicated, if you have, one splice located between the near end and midpoint of the, cable system. Now, in this case, the fourth case, we are considering a joint at a distance which is less than the 50% of the cable length. So this is the cable length, total cable length. This is the joint location, which is clearly you can see less than 50%. So here a dotted line is drawn to draw the reflections under. Now you can see from here a wave started and it is reaching the splice here, joint here, and this is the first reflection. Again from here it gets reflected again. Then this is the second reflection. Then it goes on like this actually. So you can see how many number of times it got reflected. So this is actually the first one is the location of the giant actually splice. But this is one dubious reflection. So it's not actually representing the a giant here. This also not reflecting the giant here. These are all due to reflection of the reflections. Because the giant is located less than 50% of the distance, then here there is one reflection, and due to that again it gets reflected here. Only you observe the lesser magnitude here, and then again even lesser magnitude further actually. So the magnitudes are different, you can see. There may be some dispersion also, the attenuation, both also. So, but this is the only giant. These two are not the giants. So this is these two are called actually ghost reflections. So at least one TDR ghost reflection will be observed, depending on the distance actually, at which place the splice is located under. Generally easy to interpret, taking into account the attenuation and dispersion. We can see, the by studying the first reflection, if it is multiples of this first reflection, the distance or time scale, then obviously we can identify that these are the ghost reflections due to the first splice only. And normally we have the data of cable systems actually, unless a cable is buried 50 years ago. So in that case, maybe sometimes their data may be lost, but normally we know how many giants are there in a given cable system, because the utilities, they maintain this data actually whenever the new gianting is done under. So using that data, as well as by carefully studying the distance of first reflection and then the second and subsequent reflections, we can easily can come to a conclusion that these are the ghost reflections under. So then if it becomes more, if there are more number of slices, and until now we have considered only only one giant at different locations. Now if there are two giants here, for example, you can see the splice 1 here, splice 2 here, two giants, and you can see how complicated the the reflections are. So at least one TDR ghost reflection observed. Generally it is challenging to interpret, even by taking into account the attenuation and dispersion also. It is not that easy to interpret, because multiple reflections, and then there may be superposition of various reflections also, which will give you a complicated signal here. So it becomes challenging. If the number of giants are increased, then the complexity increases like anything. So then the case 5, considering use of impedance coupling at near end. Yeah, so what can be done? This is one of the solutions here. Now we stop the impedance, we stop the reflections at the near end by using impedance coupling. Means we use the matching impedance here, so that there will be no reflections here. So at the near end you can stop the reflections, so that there will be no multiple reflections here. But you can see here, so this is the first reflection, and this is the second reflection, and this is the third reflection due to the reaching the far end. Now you can see these are multiple reflections here which are occurring, but which are not entering into the this thing. So we have to, if we use proper coupling in the input this thing, then you can avoid these kind of ghost reflections. But if the matching is not perfect, because cable impedance may be different for different cases. If the matching is not perfect, obviously you are going to end up in several reflections like this. All TDR pulse reflections are observed at the near end when you use the coupling, impedance coupling. No ghost reflections are observed in the TDR trace before far end reflections. The presence of ghosts is still possible depending on the splice or anomaly location or separation. So that's why often it requires an expert advice. What is happening inside for an interpretation. So those who understand this wave phenomena, these reflections, etc., is needed for understanding the time